All right, so I guess it says both a recap video and an actual lab video. Um, I'll be going through both osmosis, kind of scientific method, and a little bit of the surface area to volume relationship or ratio. So what we were testing in lab is we were taking basically goldfish, we were putting them in different salinity waters from freshwater to saltwater, and then we were measuring the percent change in their body mass. So what we were trying to do is we were trying to determine whether they were osmoconforming, so whether they were just passively sitting in their environment and they were just allowing solutes and water to flow in and out of their body, or we were trying to see if they're an osmoregulator and then actively regulating the amount of solutes or water inside of their body. So I guess as a little bit of the experimental design, we had 8 goldfish sitting in these bowls of either freshwater or saltwater. And so the saltwater was either 15 parts per thousand, so if you think roughly 1.5% salt, and then the freshwater was deionized water, so water that's been stripped of all salts, metal ions, basically anything you can think of. And so it should have just been pure water, so H2O. So we put the goldfish in there, and then we let him sit for 20 minutes after measuring them, or weighing them, I guess would be a better term. And so we let him sit for 20 minutes, and then we measured him again, and then we calculated the percent change per individual, and then we averaged that out. So going back to that question, whether it's an osmoregulator or an osmoconformer, we could really ask a couple, we can really present a couple hypotheses for our experiment. So for the first, I guess, hypothesis, we could ask, we could state, is this goldfish a osmoconformer? And so you present alternate hypothesis that no, it's not. So you have those two hypotheses that the goldfish is an osmoconformer or it's an osmoregulator. You could also present hypotheses based on if it's an osmoconformer. So if it's an osmoconformer, using what you know now from the lecture video, will that goldfish be losing mass or gaining mass in the saltwater or the freshwater solutions? And then if it's an osmoregulator, what will happen to that goldfish? Will it lose weight, will it gain weight, or will it stay the same in either one of these solutions? So those were the general principles that we were working with goldfish. We were also working with potatoes. So we had 2 different sized potatoes. We had small potatoes and large potato pieces. And then we were dropping them in freshwater or saltwater, and we were measuring, once again, percent change that occurs over 20 minutes time period. So the whole purpose of that wasn't so much to see whether it was osmoconforming or osmoregulating, but rather to see if it was, or if surface area to volume ratio was having an influence on the amount of weight lost. So once again, we're working with osmosis, and so with saltwater, we could kind of expect, if this organism is osmoconforming, that there's more solutes, so just material that's dissolved inside of the water. So in this case it was salt, so sodium chloride. There's more sodium chloride dissolved outside the body than there is inside the body. And so because there's more solutes at a higher concentration outside the body of that goldfish than there is inside the body of that goldfish, freshwater, once again, this is if that goldfish is an osmoconformer, that freshwater is going to leave the body and move to that higher concentration of solutes. So there's really 2 ways you can picture this. So the first way is that water is moving against the concentration gradient of solutes. So there's more concentration, or a higher concentration of solutes outside the body than there is inside the body. So water is going to leave the body that way. Or you can think of it as there's less pure water outside the body than there is inside the body. And so that water is going to follow that concentration gradient from low to high that way. I personally think it's easier to think of it in terms of solutes, so the amount of salt outside versus inside. but it's really how you want to remember it. So this fish is going to lose weight because all that fresh water is now leaving its body. I guess I should probably change it so it's not triple X. So in the case of freshwater, where there's more solutes inside the body than there is dissolved outside the body, freshwater is going to be flowing inside the body, and so this fish is going to be gaining weight in terms of fresh water. So once again, water is going against the concentration gradient of solutes. It's moving from low concentration of solutes, freshwater, to a higher concentration of solutes inside this fish. That's if our fish are osmoconforming. If they're osmoregulating, the same process is probably going to be happening, whether it's water flowing into the body or water flowing out of the body. But this fish is then going to be actively regulating the amount of salt. And so what's going to happen, where's another marker, is that this fish will use it will start uptaking sodium chloride, so salt, just passively. So as it's swimming along, it's just going to be taking in salt. It's going to be accumulating it in its kidneys and then excreting it out as urea or urine in the form of ammonia. Or through its gills, it's going to be pumping out sodium through what we would consider a sodium ion pump. So it's basically trading hydrogen ions for sodium, and so it's just continuously pumping these salt ions outside of its body. And the same thing kind of goes with freshwater. So these fish are just constantly swallowing water. Water is just passively flowing across that semi-permeable membrane. And so they have to get rid of it somehow, and usually the form is urine. So that's kind of the basis of what we would be talking about in a little bit. So back to the experimental design, we had multiple bowls with saltwater and freshwater. We had 4 of each. And so we formatted our data. Move the camera for a bit. So we formatted our data to look something like this. So we had our starting weight and our ending weight. So we had our starting weight right here. We recorded the beginning weight for each fish before we started dumping these fish inside, well, salt water. So this is the starting weight for each of these goldfish in freshwater. So right now they're in what we would consider a hypotonic solution. So there's more solutes inside the body than there is outside the body. So freshwater, if this fish is an osmoconformer, that freshwater will be flowing into the cell walls. Right here we have a saltwater solution. Once again, we have 4 different goldfish. And so they're sitting in a hypertonic solution. So there's more solutes inside the body, or I'm sorry, there's more solutes outside the body than there is inside the body. So that goldfish should be losing, that goldfish should be losing body mass in terms of fresh water flowing outside of its cells. I guess I should mention, before we put these goldfish in the saltwater and the freshwater, they're sitting in what we would consider an isotonic solution. So they're sitting in basically an aquarium that they have been accustomed to for several days, and so they shouldn't be losing salt or they shouldn't be gaining water over that time period. So it was, I guess, a stark difference to put them in a freshwater solution or a saltwater solution. So after 20 minutes, we measured them again. We removed all the excess water. We set them on a scale. We measured basically the change that occurred over those 20 minutes in terms of mass. So those values are written in this column labeled end. So we have these 4 values right there, which sort of are ending weight. So the next thing that we did is we calculated the percent change over that 20 minutes for each individual. And so the reason why we don't just subtract 1.9 from 1.5 and then average that out per the entire column is that each of these fish started off with a different weight, and so you'd be you wouldn't be comparing everything across the same standard. So by taking the percent change, where we basically standardize everything by each individual's weight, we're able to compare across values. So to calculate percent change, raise the video a little bit. To calculate percent change, we just take the ending value. We take the ending value, we subtract the starting value, then we divide it by the starting value, and then you multiply by 100 to get, well, a percent. So for this value, well, I'll work through the first row for you. So for percent change for this row right here, we have our ending value of 1.09 minus our starting value of 1.05 divided by our starting value again, which is 1.05. Then we're going to multiply that by 100 to get our percent. So I don't have a calculator up here, so I'm not going to do the math. Well, I've already done the math, but I'm not going to show you. So 1.09 is 0.4 divided by 1.05 is roughly 3.81%. And so you're going to do this for every single column in this table. So from each of these rows, and for the saltwater too, you're going to calculate percent change. And then once you've gotten all these rows filled in, what you're going to do is you're going to take the average of those 4 rows. So basically adding each one of these cells, so 1, 2, 3, and 4, add those 4 values up, and then divide by 4, and that will give you the average. You do the same for saltwater, so 1, 2, 3, 4, and you're going to put the average right there. So the average should be able to tell us whether these fish are gaining mass, losing mass, or neither of the two. If that mass is staying the same, or, yeah, well, I guess those are really the 3 options. So I guess one thing to note about the percent change is that you can have a positive or negative value. So before I let you all fill in the rest of this chart, I'll work through one of the saltwater examples for you. So once again, we have our ending value, 0.54. So 0.54. Subtracting our starting value, which is 0.65. And then we divide again by our starting value, 0.65. So you have a negative value up top, so you have negative 0.909. Then you're going to divide it by the starting value, and so that's still going to have a negative value. And so that's indicating that you actually lost weight, so you have a negative percent change. And so this ends up being negative 16.9%. So I'm going to give you, I don't know, a minute to, well, I guess pause the video and then work through the percent change for each of these cells. And then when you're finished with that, I guess press play and compare your answers to the answers that I read on the board. So I guess now that you've finished your table and you've filled in all the values for the percent change for each of the goldfish, once again, what you want to do is you want to calculate the average. So you want to add all 4 of these cells up and then divide by 4. So that'll give you the average or the mean, however you call it. So I'll give you another couple seconds to, well, let you pause the video, fill it out. You should be good. All right, so now that we have our average values for percent change in freshwater and percent change in saltwater, we can start to make some conclusions. So in past labs, I've had people go through actual process of making a t-test, but that ends up taking way too much time. So instead, we're just going to kind of compare these based off of means. So our freshwater solution ended up gaining roughly 7% body mass in average. So let me percent so you guys don't confuse that for grams. On the other hand, our saltwater solution, or the goldfish in the saltwater solution, almost lost 20% on average in terms of body mass. So from this data, or these data, we can make the conclusion that, well, one, our goldfish are not osmoregulating. They're actually osmoconforming, because if our goldfish were osmoregulating, we wouldn't see a net change in body mass. So the percent change for the goldfish in saltwater and the percent change for the goldfish in freshwater would be zero, well, for both. Instead, we have roughly 7% and we have roughly negative 20%. So water is flowing across that against that concentration gradient of solutes against salt. And so in that freshwater, in that pure deionized water, there's more solutes inside of that goldfish's body than there are outside. And so this goldfish is going to be gaining weight in terms of that fresh water that's flowing into its cells. In that saltwater solution, that goldfish is going to be losing roughly 20% of its body mass because it's sitting in pure salt, well, not pure salt water, but it's sitting in a pretty salty solution. And so there's more solutes outside of its body in the external environment in that solution than there are inside of its body. And so water is going to be flowing, once again, across that, or against that concentration gradient. So it's going to be flowing outside of the body. So we can consider our goldfish as osmoconforming as compared to osmoregulating. All right. So the next thing that we did in lab is we had these potato chunks, these potato squares. And so that was really to highlight what we would consider the surface area to volume relationship. So small things are much different than large organisms. So if you compare a mouse and an elephant, the mouse is going to have higher metabolism. It's going to require a higher caloric intake compared to its body mass compared to elephants. Smaller organisms also lose heat a lot quicker, and so they have to kind of keep moving. They have to stay awake all the time, keep their metabolism up. So organisms are always trying to kind of get around this rule of surface area to volume relationship. And so kind of the basis of the surface area to volume relationship is what we call the cube rule. And so if you take a cube, so of six-sided, well, 6 even squares, and you keep adding on extra layers to it, you're going to have basically a relationship between surface area and either volume or area, depending on how you want to say it. So if we take our cube and we just have a unit or some random unit and a length of 1 for a side, we can take and we can calculate area of that square, and we can also calculate volume. So I guess I should probably change that before I confuse myself and other people. So we use V for volume. So to calculate volume, you're going to take each side, so length times 3, or length times length times length. So instead of length times 3, like I just said, which is wrong, we're going to take length cubed. And so for this first square, we have 1 times 1 times 1. So area volume, I keep confusing myself, is going to be one, and then whatever units, inches, meters, kilometers, miles, whatever. Surface area, on the other hand, has 6 in front of it because there's 6 sides to this cube. So 6 times 1 squared is 1, 6 times 1 is 6. If we double our cube, so if we take the length of that first cube and we double it, so now it's 2, we now have really twice, twice the size of the length, but we now have 3 times the size of the volume. So, well, that was incorrect. Yeah, I don't even know why I said that. So, I guess moving on a little bit, if we want to calculate volume, you take 2 times 2 times 2, or 2 cubed, and so that will give you 8. Once again, whatever units you want, inches, miles, squared, kilometers, whatever, centimeters. If you want to calculate surface area, you need to take 2 squared, so that's 4, and then you need to multiply that by 6. So that gives you 24. If you want to jump ahead to a cube with 4 sides, instead you'll have, for volume, 4 times 4 times 4, which, let me double check my mental math, is 64. And then surface area, which is hidden, surface area is equal to 96. So you have 6 times 4 squared. 4 squared is 16. Times 6, you have 96. If we do this for a 6, so if we take the length of our original cube, we multiply it by 6. And so now we have a 6-sided cube. I didn't feel like drawing that out. But you can imagine that 6 cubed for volume is fairly large. Change that to V. So we have 216. And then surface area is 36 times 6. So you get 216. And so if we were to extend this out over, I don't know, 100, that was terrible writing, ignore that. But if we were to extend this relationship out over a series of increasingly larger and larger squares or cubes, we would see that at some point volume increases greater than exponentially, so it's increasing basically at a cubed rate, and surface area is increasing at a much slower rate. So once we get to 6 times the original length of our cube, both surface area and volume are roughly equal to each other. Once we get to 7 times the original length, so let me just do the math real quick. So the internal surface area, or the internal volume of a 7-sided cube, or 7 times L, so 7 times the original size of our cube, be 343. The surface area would be 294. And so this is where you start to get volume increased exponentially, and surface area increases at a much slower rate. All right. So hopefully that made sense. And so what we did next, using basically what I just talked about, that cubed rule, is we took a series of potatoes. What we did is we just took basically a large potato, and we took a smaller chunk of potato, we submerged it in salt water, and we submerged another piece, similarly large and small, in fresh water. And so what we're trying to elucidate here is that smaller organisms, so that small potato, they have a much harder time maintaining a osmotic or some sort of osmotic balance, some sort of homeostasis within their body because they are so small. So if you want to put it in, I guess, the simplest of terms, that smaller potato, that smaller organism, has a much lower distance from the outside environment to the very center point. So it has basically a much lower surface area to volume relationship. That larger piece of potato, that larger organism, has much more material, much more cells that are separating its center point from the outside environment. And so this is why smaller organisms don't have like a circulatory system, they don't have a really complex digestive system, and they don't have a really complex respiratory system, because everything that they need just diffuses into their body, and it can reach the amount of, it can reach as much cells as they need it to. Larger organisms have a much more difficult struggle because they have to increase surface area, so either through our arteries, through our lungs, increasing surface area that way, or just by having a fairly branched digestive system like the planarians do. So they're increasing surface area, trying to beat this surface area to volume ratio or relationship that we just talked about. And so that surface area to volume ratio kind of ends up structuring all sorts of life forms that we see in this lab. So I think it was Galileo or Da Vinci, one of the two, I guess, Enlightenment thinkers. I don't even know if that's Enlightenment. One of the Renaissance people, they were quoted, or they wrote down in one of their notebooks, that there is no such thing as like as a giant who is 10 times the size of a man, because of this surface area to volume ratio. So our bones grow at a certain rate. They basically are growing in a cylinder, especially our leg bones are growing in a cylinder. And so at a certain point, those bones become unable to bear the weight of our body, that increasing volume. And so those bones end up shearing or buckling or whatever. They end up fracturing under the stress of supporting that much volume. So this is why, like, elephants can't jump, because if they did, they would just shatter their bones. It's because they have such a high mass and such a high amount of volume that they would be landing on these structures, these structural supports. Whereas if you take like a mouse and you chuck it off a bridge, it'll probably survive because it doesn't have that much mass, it doesn't have that much volume that could land on the ground. So surface area is a struggle that all animals have to deal with, and how it relates back to salinity is that those organisms that are fairly small have a much more difficult time keeping solutes inside their body, much more difficult time keeping fresh water inside their body when they're immersed in a saltwater solution. If you take that same small organism, that same small piece of potato, and you chuck it in a saltwater solution, it's also going to have a difficult time keeping fresh water inside of its body, just because all that fresh water is immediately going to be sucked out from every single one of those cells. If you take that larger piece of potato, it's going to happen at a slower rate because that potato is not osmoregulating, it's an osmoconformer. If we had like a red potato, one of those really small potatoes where the skin wraps all the way around it, that would actually probably osmoregulate because it is a plant, it's living in the soil. It's not quite dead yet. But everything else, especially the potatoes that we have, they're osmoconformers, so they'll be losing weight or gaining weight depending on the solution that we put them in. So I think that was the gist of this week's lecture or lab video, lab experiment. I'm 90% sure. If I forget something, that's on me. So I'll see you guys next week.